Hi everybody, welcome back. What we're going to do today is focus on Chapter 10, Section 2. So we're talking about Section 10.2. And what we do in this section is talk about dealing with non-quantitative data and how we can analyze that when it's put into what we call two-way tables. Let's jump right in and you'll see what I'm talking about. First of all, we're still talking about relationships between variables. And the reason why we're talking about relationships between variables is because when we discover there is a relationship between two variables, we're essentially able to predict one value of one variable by knowing the value of another variable. Here's an example just to make that more clear. We were looking at correlation coefficients when we were dealing with quantitative variables. So two quantitative variables would be hours spent studying and GPA. And that's because when we look at these numbers, they have some type of numerical meaning, like hours spent studying. If you spent 10 hours studying this week, 10 actually has some numerical meaning. Makes sense quantitatively. So let's look at how those variables are related. We discussed that this would probably be, between these variables, a good example of a positive correlation, and that the two variables are moving in the same direction at the same time. When hours spent studying increases, GPA tends to increase. And the flip side of that makes sense too. When someone spends less hours, fewer hours studying, their GPA tends to be lower. So essentially we're able to predict someone's GPA to at least some extent by knowing how many hours they spend studying. Now, of course, the stronger that relationship, the better the prediction. In reality, this relationship is modest. The correlation is somewhere around maybe 0.3, 0.35. So we're only able to predict someone's GPA with so much accuracy by knowing how many hours they spent studying. That's just a little bit of background about what we're talking about with these relationships. Well, what about when we're dealing with non-quantitative data, when we have variables in which the data does not have numerical meaning? Here might be an example right here. One variable might be the person's smoking status, whether they smoke or not. And the other variable would be the person's cancer status, whether they have cancer or not. And you can see there's nothing quantitative about that. Smoking status is you smoke or you don't smoke. There are no numbers involved. Cancer status, you have cancer or you don't. There are no numbers involved. So if that's the case, we can't compute a correlation coefficient, that R coefficient that we computed previously. But we are going to be able to compute what we call a chi-square statistic. And this is a chi-square symbol right here. And of course, the chi is another Greek letter. So we're going to be organizing our data into what we call these 2x2 contingency tables. And this is how it would look with this example when we're looking at people's cancer status and their smoking status. The reason why we call it a 2x2 table is because we're dealing with two variables and each of them have two levels. So it's easy to get confused because you see three columns and three rows, so it seems like it's a 3x3 table, but in reality this last column right here and this bottom row right here just represent totals. So there's no new information in this column and in this row. It just summarizes the information from the key columns and rows. So the key columns would be representing a person's cancer status, whether they have cancer or not. So there are two levels of that one variable. And our other variable, your smoking status, has two levels as well, non-smokers or smokers. So you can see that's why we call it a 2x2 contingency table. And then we're able to put everybody in their appropriate cell. So there were 220 people overall in this study. We can see that 45 people are non-smokers who have cancer, 60 people are non-smokers who do not have cancer, 75 people are smokers who have cancer, 40 people are smokers who do not have cancer. So bottom line is these tables do a really good job of organizing our data, and from there we can analyze to see if there's some type of relationship such that we can predict somebody's cancer rate by knowing if they smoke or not. That's what we want to determine. Is there a relationship between those two variables? Because if there is, to at least some extent, we can predict one variable from the other. So let's talk about this in a little bit more detail. Let's just identify, kind of looking toward the future here, what our null hypothesis would be, what the alternative hypothesis would be, and then some other basic information to make sure we know how to read this table. Let's first talk about that null hypothesis. The null hypothesis is always, regardless of what test we do, talking about how we would see the data if there was no relationship, if there were no differences. So in this case, the null hypothesis would state that there's no relationship between smoking status and cancer status. Another way to put that is that the two variables are completely independent. Knowing the value of one variable gives you no prediction toward figuring out the value of another variable. So if they're completely independent, it doesn't matter if you smoke or not in terms of determining your probability of getting cancer or not. Now, of course, the alternative hypothesis would state that there is some type of relationship. So there is a relationship between smoking status and cancer status such that smoking status influences cancer status. So there is some type of relationship. That would be the alternative. So we always have these two competing hypotheses. All right, that's just like we were working with before. Let's make sure we better understand how to deal with this table and make sense of the numbers. So here we're talking about just some of the basic background information. So let's compute a few things first, just to make sure we can look at the table and pull from it the numbers that we need. So for example, what percentage of non-smokers had cancer? Well, this row right here shows all of the non-smokers. So there are 105 non-smokers. We want to figure out what percentage of the non-smokers had cancer. We can see that 45 of these 105 people had cancer. So we can work that out real quickly. Let me pull up my calculator. We'd have 45 people divided by 105. That equals 0.428. We'd call that 0.43 or 43%. So I've got the calculation listed right here. Let's go ahead and just go through these real quickly just to make sure we can answer these questions, because we just simply want to be able to understand how to draw information from these tables so that we can interpret our results. So what percentage of smokers had cancer? Here, all the smokers are listed in this row. There are 115 of them. We want to figure out what percentage of them had cancer. There were 75 out of the 115. So again, we'll have the exact same type of layout as we had before. Now we've got 75 divided by 115. So we can use our calculator again. 75 divided by 115 equals 0.65 or 65%. What percentage of all subjects had cancer? Well, in these tables, the lower right cell always shows the total number of people overall in this particular study that we're dealing with. Because we can see that this adds up the non-smokers and the smokers. So that would list everybody, smokers and non-smokers. And then even when you look at it with this row, this is all the people with cancer, all the people without, add them up, that equals 220. So this is the number of people overall. What percent of all subjects had cancer? There are 120 people with cancer out of 220. So we'll take 120 and divide by 220. That equals 0.545, so we're talking about 55%, 0.55. What percentage of those with cancer are smokers? So you see, we're just looking at the table in a variety of ways, making sure that we can answer these questions by looking at the table. So what percentage of those with cancer are smokers? Here are all the people with cancer. There are 120 of them. We want to know what percentage of those are smokers. 75 out of the 120 are smokers. So let's figure that out. We've got 75 divided by 120. That equals about 63%. 75 divided by 120, again, 0.63. What percentage of those with cancer are non-smokers? So here again, we have all the people with cancer. 45 of them are non-smokers, so it's 45 divided by 120. So 45 divided by 120 equals about 38%, 0.38. All right, so we just wanted to make sure that we can do some basic work with those tables. Now we can take this to the next step. So again, when we do hypothesis testing, which is where we're working toward, we always start by assuming that the null hypothesis is true, that there are no effects, no differences, no relationship, in this case, between the two variables that we're looking at, smoking status and cancer status. Well, then the question becomes, how would the frequencies in this table be distributed if there was no relationship between those two variables? Because, of course, if we want to determine if there is a relationship, we need to determine how would the data look if there is a relationship. Well, we start by determining how would the data look if there's no relationship. It's really an easier way to look at it. So, in other words, what are the frequencies that we would expect in here just by chance if there's no relationship between those two variables, cancer status and smoking status? Well, one thing that's not going to change here are the total number of non-smokers and smokers that we had, or the total number of people overall that we measured. Of course, all these totals remain the same. How many people in the study had cancer? We can't change that. There were 160 people with cancer. How many people had no cancer? There were 240. So when we try to determine what these values would be just by chance, these column and row totals always remain the same because we're not going to change the number of smokers and non-smokers. We're not going to change the number of people with cancer or no cancer. We simply want to see how would those numbers be distributed if indeed there was no relationship between cancer status and smoking status. So let's just think about it intuitively for a second. There are equal numbers of non-smokers and smokers, 200 of each. And we know that 160 people in this study have cancer. If there's no relationship between smoking and cancer, and there are equal numbers of smokers and non-smokers, wouldn't we expect these 160 people who have cancer to be distributed evenly among the smokers and the non-smokers? Well, if they are, 160 people divided evenly between these two groups would be 80 and 80. So we can stick in those numbers. Now, one thing you'll see is once we figure out the value of one cell, we can pretty easily figure out what the values of the other cells would be because all the totals need to match up. So for example, once I knew that this cell was equal to 80, I know that this must equal 80. We also know that this must equal 120. So it becomes easier to kind of check our work, but we always want to make sense of things. So for example, if these 240 people who do not have cancer are distributed evenly between these cells, we would expect 120 in each cell. So we can stick those numbers in there and we can see that it makes sense. 80 plus 120 equals 200, 120 plus 120 equals 240. So it makes sense. And one reason why it makes sense so easily is because we're using very easy numbers and we have equal numbers of people in these groups. Let me give you an example that's a little bit harder. Let me just explain also the notation. These are the expected frequencies. F just represents frequencies. The little sub E represents the expected frequencies. So these are the frequencies we would expect to find if there's no relationship between smoking status and cancer status. They'd be divided up essentially equally because they're equal numbers of smokers and non-smokers. But check out this example now. Let's just assume that we had twice as many smokers as non-smokers in this study. So there were 600 people overall. And let's just assume that these numbers are correct as well, that 150 of those 600 people had cancer, and then the remaining 450 did not. Now, how would those numbers be distributed if indeed there was no relationship between smoking status and cancer status? So again, these are the expected frequencies, the frequencies that we would expect if the null hypothesis was true, that there's no relationship between the variables. Well, let's just look at it intuitively. That's what we're doing here on this particular page. We're just looking at these expected frequencies intuitively. So here we can see of the total people involved, 600, 1/3 of them are non-smokers, 2/3 of them are smokers. So that would mean that if there's no relationship between smoking status and cancer status, these 150 cases of cancer should be distributed using these same proportions. 1/3 of those cases should go to the non-smokers, 2/3 to the smokers. 1/3 of 150, you might be able to just see in your head, is 50. And if we didn't see it in our heads, we could always just take 150 and divide by 3. We can see that it equals 50. So I'll stick that number in. Now, of course, once I know this value, I can easily predict what these other values would be. This is going to have to be 100, and 100 is 2/3 of 150. We can work that the same way. 1/3 of the non-smokers should come from these 450 who do not have cancer. So 1/3 of 450 equals 150, and what would be left? 300. And again, the numbers make sense. 50 and 150 equal 200, 50 and 100 equal 150, and we could do the same thing going down here and going across this way. But now there's a problem. Although that was relatively easy, we're also dealing with these nice round numbers. I mean, these are nice round numbers, and in the real world, it doesn't typically work that way. So the intuitive method that we're using can become very difficult. So we want to have some type of formula where we can figure out these expected frequencies without having to rely on our basic intuition. Let's talk about that next. Here's a little formula that we're going to use. And again, this represents the expected frequencies. What this is saying is in the numerator, take the frequency for the row that you're interested in, multiply by the frequency for the column that you're interested in, and then divide by your overall sample size. We'll go through it and you'll see exactly what that means. So let's first carry over some of the numbers that we were dealing with before, so you can see that we will replicate them using this formula. So in the first example we looked at, there were 200 non-smokers, 200 smokers, 160 people out of the 400 had cancer, 240 out of the 400 people did not. All right, how can we find these expected frequencies using this formula? Well, let's look at this cell right here, and I typically kind of number these cells, just my own little numbering system. I always see this as cell 1, this is cell 2, this is cell 3, and this is cell 4. So let's look at cell 1. You can see that this is the intersection of people who have cancer and people who are non-smokers. So I'm looking at this column and I'm looking at this row. So in order to find this value using this formula, it says take the frequency for the row. So for the whole row, I have 200 people. It says multiply that by the frequency for the column. For this column, I have 160 people. And then divide by your n, your sample size. You might recall that in this corner right here, it always represents the total number of people we have. So this is saying take 200, multiply by 160, and divide by 400. Let's just do that real quickly. So we will take the frequency for the row, 200. We will multiply by the frequency for the column, 160. And then we will divide that by 400. That equals 80. All right, well, that's the same value that we got previously, just based on the intuitive method. Now, again, let's say we're looking at this particular cell. Now we'd look at the frequency for the row. Again, it's 200. The frequency for the column, again, it's 160. And then divide by 400. So in this case, it would be the exact same analysis. So we can see that it's going to equal 80. Let's look at this cell right here. The frequency for the row is 200. The frequency for the column is 240. And then we would want to divide by 400. Let's work that out real quickly. So we take the frequency for the row, 200. We multiply by the frequency for the column. We're dealing with this column. So we multiply by 240. The value that we get is 48,000. We want to divide by our n. That's what the formula asks us to do, divide by n. So I divide by 400. That equals 120. So that's the same number that we got using the intuitive formula. Then, of course, to find this cell right here, we take the frequency for the row, 200, multiply by the frequency for the column, 240, then divide by 400. Well, that's the exact same thing we just did. So that equals, again, an expected frequency of 120. All right, so the formula that we're dealing with right here works. Let's get one more bit of practice with it. Let's look at the totals that we were dealing with previously, and let's figure out these values. Again, the way that I number the cells typically is cell 1, 2, 3, 4. So let's deal with cell number 1. In this row right here for this cell, we have a total of 200. In the column, the total is 150. So we're going to take 200. We're going to multiply by 150. We find a value of 30,000, and then we divide by our n. And in this case, our n equals 600. Remember, our n is always listed in this lower right corner. So now I divide by 600, and the expected frequency equals 50. So we can stick that in. Now, we figure that this is going to equal 100. It only makes sense. Let's make sure that our formula gives us that value. So in this particular case, we're going to take the frequency for the row, that equals 400. We are going to multiply by the frequency for the column in question. That's right here, 150. So I multiply by 150. That's a value of 60,000. I'm now going to divide by my n, which equals 600. And that equals 100, just like I expected. So I'll just fill in the other values, but you can see the formula works. So we can easily find the expected frequencies. These are the frequencies we would expect to find just by chance. There's no relationship at all between smoking status and cancer. All right, well, let's talk about where we're going to go from here. As I mentioned, these are the frequencies we would expect just by chance. That's what this says right here. Now, if we find that there's a big difference between our observed frequencies, I mean the actual frequencies that we measured, and these frequencies that we would expect by chance, then we have some good evidence for rejecting the null hypothesis. Because remember, the null hypothesis is based on these expected frequencies. That null hypothesis is showing no relationship. If our actual numbers differ quite a bit from these expected numbers, it's good evidence that there is a relationship and that we would reject the null hypothesis. So how much evidence do we actually need to determine if we can reject the null hypothesis? That's what we're going to talk about next. So this brings us to the chi-square test of independence. We want to test to see if these two variables are indeed independent. If they're independent, in this particular case, your smoking status would give me no information on predicting your cancer status. Well, the null hypothesis states that they are independent. I want to see if I can reject that. So our first step is to compute the expected frequencies. These are our observed frequencies, the actual frequencies based on the study that we conducted, based on the data that we collected. So here you see an F representing frequencies with a little sub O for observed. These are the observed frequencies. So again, we're finding that there were 50 non-smokers and 50 smokers. But let's just take a look at this for a second. Here it's showing that 10 of the non-smokers had cancer out of the 50, but 36 of the smokers out of the 50 had cancer. So that's the actual data that we're finding. Well, let's see, what would these numbers look like? How would they be distributed if indeed there was no relationship between smoking status and cancer status? So that's what the expected frequencies are all about. So let's just quickly compute them. Again, the totals are always going to remain the same. It's not like we're changing the number of smokers and non-smokers who are in the study. It's not like we can change the number of people who had cancer or non-cancer, but we can kind of think about how would those numbers be distributed if indeed there was no relationship between those two variables. So again, we can use our formula. We can look at cell 1, cell 2, cell 3, cell 4. If I'm looking at cell number 1 right over here, I want to look at the frequency for the row, the total frequency for the row, that equals 50, the total frequency for the column, that equals 46. Multiply those and divide by 100. Let's work that out real quickly. So the frequency for the row equals 50. We multiply by the frequency for the column, which is 46. That gives me a total of 2300. And now I want to divide that by my n, which is equal to 100. That leaves me with the value of 23. So right here, we have an expected frequency of 23. Once I know that number, as long as I computed it right, I can compute the other ones pretty easily as well. So that should equal 23 because 23 and 23 equals 46. We can predict right here that this should equal 27, right? Because 23 plus 27 equals 50. Let's use our formula to make sure. It's always smart to use your formula to check your work. So let's look at the frequency for the row is 50. Frequency for the column is 54. We'll multiply those and divide by 100. Let's work that out real quickly. So we'll take 50. We will multiply by 54. That equals 2700. We'll divide by our n, which is equal to 100. And yeah, we get a value of 27, just like we expected. So we have 27 in there and 27 in here. All right, this was pretty easy to determine even based on the intuitive method, but that's just because I'm giving you some nice easy numbers. So now you can see what's going on. Here is the actual data. Here is the data we would expect to find just by chance if indeed there was no relationship between cancer status and smoking status. So if there are big differences between these observed frequencies and these expected frequencies, it's pretty good evidence that there is indeed some relationship between these two variables. So that's what we're doing. We're checking for a departure from the observed data and the data we would expect if the two variables were completely independent. The way we do that is by using this formula right here for a chi-square test. Let's talk about how it works. We see the sigma sign. The sigma sign is telling us that we're going to sum something up, so we're going to add stuff. This is a pretty easy formula. Once we work through it, you'll see how it works. Once you get a little bit of practice, you'll see that you can do it without much of a problem. It's saying take the observed frequency and subtract its associated expected frequency. This is where my little numbering system really kind of helps out. Because if we see this is cell 1, this is cell 2, this is cell 3, and this is cell 4, we can see that over here is the corresponding cell 1, cell 2, cell 3, cell 4. So you take the observed frequency, for example, in cell 1, you subtract the expected frequency, again, from cell 1 over here in the expected table. We're going to square that difference and then divide by this expected frequency. And then to that we add the exact same thing that we just went through, but for cell 2. So the observed frequency, 36, subtract its associated expected frequency, 23, square that difference. See, it's calling for us to square this difference, and then divide by the expected frequency, 23. Then we'll go on to cell 3. Take cell 3's observed frequency, subtract cell 3's expected frequency, square that difference, divide by that expected frequency. Well, we need to do that for all 4 cells. So this is how this would look. We can kind of walk through it again. So here's the observed frequency of 10. I'm subtracting the expected frequency right here of 23. We're going to subtract those, square it, and then divide by this expected frequency of 23. It's exactly what the formula is calling for. Then it says add to that exact same algorithm, that exact same pattern of data for the next cell. So here's cell 2. So we take 36, that's the observed frequency. We're going to subtract 23, the expected frequency. We're going to square that difference and then divide by the expected frequency. Then add to that for the third set of cells. So we take the observed frequency of 40. We subtract the expected frequency of 27, and then we divide by 7. Take the observed frequency of 14, subtract the expected frequency of 27, square that difference, and then divide by 27. So I've got that all laid out right here. So let's work this out a little bit together right here just to make sure that we understand what we're doing. So 10 minus 23, that's pretty easy. 10 minus 23 equals negative 13. But we're going to square that value. I don't have a square button on here, so I'm just going to multiply by 13, and I'll go ahead and just make it negative. We know it's going to be positive, though, right? Because anytime you square a value, it's always going to turn out positive. So that equals 169. 169 divided by 23. All right, so let me just take you the next step of the way down with this equation. You can see that we've computed 169 divided by 23. Let's move over to the next part just to figure out how we got this right here. Here I took 36, subtracted 23, that equals 13. We're going to need to square that. 13 times 13 equals 169. Then we divide that by 23. So do you start to see this pattern that emerges? With the 2 by 2 tables, if we've done it right, our numerators will all work out to be the same. So that's kind of nice because it's a good way to check our work. If we're not finding that pattern, it means we're making some type of mistake. Then we're always dividing by those expected frequencies. Here's another thing to keep in mind. Because our formula is asking us to square these differences, these numerators will always be positive, always. So we can never have a negative value for chi-square. It will always be a positive value. Well, at this point, we can just go ahead and work out all these fractions. So, sorry about that. Sorry about that. Let me just catch us back up. Here's where we were. So let's work on those fractions. In this particular case, let me find my calculator. We've got 169 divided by 23. That equals 7.347. We'll just call that 7.35. To that, we're going to add 169 divided by 23. 169 divided by 23. 7.347. We usually round to 2 decimal places. We'll just call that 7.35 as well. It's the exact same thing we just worked on. Now we've got 169 divided by 27. So 169 divided by 27. That equals 6.26. And again, we have 169 right here divided by 27. And that's going to equal 6.26. Let me make a quick change on my pointer so that we can see it on my screen. There we go. All right, so now I'm just going to list those values that we just computed. We had 7.35 plus 7.35. This fraction was equal to 6.26. So was this 6.26. When we add them all up, we find a value of 27.22. Let's just verify that. So we've got 7.35 plus 7.35 plus 6.26 plus 6.26. That equals 27.22. 27.22. So that's our chi-square value. All right, so now we know what the actual chi-square value is. And again, this number is going to get larger as the differences between our observed frequencies and our expected frequencies increase. So as we have bigger differences between these two contingency tables, we're going to have a larger chi-square value. So let's see what we do with that next. So heading on back to this particular slide, we're asking how big does that chi-square value need to be to reject the null hypothesis? Well, as I mentioned, we're working with these 2x2 contingency tables. The way that we compute degrees of freedom for these tables is by taking the number of rows that we're dealing with. And remember, here there are two important rows here. The totals don't really count. That's no additional information. So we have 2 rows and 2 important columns. Well, we take the number of rows and subtract 1, multiplied by the number of columns, where we subtract 1. So 2 minus 1 is 1, multiplied by 2 minus 1 is 1. We're left with 1 times 1 equals 1. That's just kind of a long way of telling you that when we're dealing with these 2x2 contingency tables, and that's all we'll be dealing with when we cover this chapter, we will always have 1 degree of freedom. You might recall that we had to compute degrees of freedom when we were dealing with the Pearson correlation coefficient to determine our critical value, to determine how large that R value had to be for it to be statistically significant. Well, we need to know degrees of freedom in this case as well to know how big our chi-square value needs to be statistically significant. Well, here are those critical values for a 2x2 table when we do indeed have 1 degree of freedom. If we're using an alpha value of 0.05, the critical value for chi-square is set at 3.841. If we're using an alpha of 0.01, remember, then we need more evidence. We're held to a higher standard. And then we need a chi-square value of 6.635. So those are the critical values. Well, we looked at our observed data, we compared it to our expected data, and when we did that, we found a chi-square value of 27.22. That's a pretty big chi-square value. You can easily see that this chi-square value that we obtained is bigger than either of these critical values. So that shows that our result is statistically significant at not only the 0.05 level, but at also the 0.01 level. So in this particular case, we see that smoking is statistically significantly related to cancer. There is indeed a statistically significant relationship between those two variables. Now let's try to make sense of that relationship. So the only way to really do that, I think, and really understand what's going on is to compute some percentages real quickly. And we did this previously when we were just kind of looking at some numbers. If I want to know now what proportion of non-smokers developed cancer, here I've got all of the non-smokers, there are 50, 10 of them developed cancer. So let's just look at our calculators real quickly. If we just took 10 and divided by 50, that equals 0.20, that's 20%. Let's figure out right over here, what percentage of the smokers got cancer? There were 50 smokers, 36 of them got cancer. So 36 divided by 50 would give us that percentage, 72%. Now I can see very clearly, after I've actually computed that value, the direction of the relationship. And I'm sure you were predicting all along that if there was going to be a relationship, it was that the smokers would be more likely to get cancer. And of course, that's what we found based on these numbers. But it's not always that obvious. You know, of course, we need to actually compute the percentages to know how to interpret our final results. So in this particular case, we would say smokers are more likely to develop cancer. 72% of the smokers had cancer, only 20% of the non-smokers had cancer. So very clear relationship in there. So do you see what I mean about when there's a relationship between two variables? To some extent, we can predict the value of one variable by knowing the value of the other. So for example, if I'm a medical professional and I know that you smoke, I know you have an increased opportunity, an increased probability of developing cancer based on previous research. Well, let's take this whole thing now and put it into that 4-step hypothesis testing procedure that we learned about. So this just summarizes what we just found. Based on the sample data we just analyzed, is there a relationship between smoking status and cancer status in the population? So we're using sample data, trying to learn about the population. That's what inferential statistics is all about. So you'll recall that we found a chi-square value of 27.22. We're going to test this with an alpha of 0.01 because most medical examples would eventually be published in a medical journal, and medical journals usually require that you use an alpha level of 0.01 because that means over the long run, we would make type 1 errors only about 1% of the time. And again, because chi-square values are always positive, the chi-square test is actually a one-tailed test, a directional test. we have no choice. It's always going to be a positive value just because of the way the test is constructed. So let's state some hypotheses. Remember, we always have these two competing hypotheses. Our null hypothesis, if we look at it just kind of in words, intuitively, is stating that there's no relationship between smoking and cancer. What that means is our chi-square value would equal 0, because if there's no relationship between smoking status and cancer, then our expected frequencies and our observed frequencies would be the same. We would have a 0 value for chi-square. Our alternative is that the chi-square value is greater than 0, which would tell us that there is some form of a relationship between smoking and cancer. All right, step 2 for us has been pretty easy because we already did all the hard work and we have the information in our little summary above. So when it says collect the evidence, here's our evidence. We computed a chi-square test and we found a value of 27.22. Well, the important thing was now to compute the probability of finding that just by chance. Well, you recall we looked to see what our critical value was. We found a critical value of 6.635 when we're using an alpha of 0.01. This chi-square value of 27.22 is clearly inside this critical region. Remember, right in here we start with 0. Here we have our critical region beginning at 6.635. 27.22 is way out into that critical region. These are values that we would not expect to find by chance. So we have effectively ruled out chance as an explanation for our results. Well, we know that that means we have statistically significant results. So in step 4, we're going to go ahead and we're going to interpret those results. So our chi-square value of 27.22 exceeds that critical value of 6.635. So that means the probability of finding this result just by chance is less than 1%. Because the chi-square values that are this large occur just by chance less than 1% of the time. And that was all that we needed to prove. That was our cutoff point. So the result is statistically significant at the 0.01 level. Well, if our chi-square value is in that critical region, otherwise known as a rejection zone, then we're going to reject this null hypothesis. So here we would say that we would reject our null hypothesis, and we're going to conclude that smokers are more likely to develop cancer. So I'm going to come up here and more formally reject that null hypothesis and then take on the alternative. There is a relationship between smoking and cancer. Specifically, smokers are more likely to develop cancer. All right, well, that was a lot of work to get to that point, but it also provided us with a lot of information. So this is very similar to the examples that we dealt with last time with correlations. We're looking at relationships between variables, but I hope you're seeing here the variables that we're dealing with now are non-quantitative. There are no numbers involved, but we can still determine if there is a relationship between those variables. And here we realized that people who smoke are more likely to develop cancer. Let's go through another example. We'll kick it up a notch. Let's use some real-world data. And because we're going to be using some real-world data, we'll round things off just a little bit easier, just out to 1 decimal place, just so our math is a little bit easier to compute. In general, on exams and things like that, I give you much easier numbers to use, but I wanted you to see a real-world example so that you can see how we come up with these results. This was a very famous study looking at women. They were all actually nurses, and they were involved in an experiment where half of them were randomly assigned to take hormone replacement therapy. All of these women were candidates for hormone replacement therapy because they were having symptoms, like of being postmenopausal. So half of them were randomly assigned to take hormone replacement therapy, and the other half received a placebo. So they were in the control group. You can see we had lots of people in this study, over 8,000 people in each group. So 16,000 of these women overall. And what we were really interested in learning, what the researchers were really interested in learning, was a variety of things, but one thing they measured was if these women had coronary heart disease. So that's how they refer to this, as coronary heart disease. I think it's often referred to as coronary artery disease as well, but we'll use the same language that they used. So here we can see the number of people overall who had heart disease, the number of people who did not, then the number of people who were taking the hormones, the number of people who were in the control group. So we're trying to determine, is there a relationship between hormone replacement therapy and heart disease? Now, of course, that relationship could go in one of three, I guess, directions. First of all, there could be no relationship at all, right? That would be one direction, if you want to call it that. The other direction is that taking hormones could lower your odds of heart disease. And then the third possibility is that hormones could increase the odds of heart disease. So we want to determine what's going on. That's why we're going to do this chi-square analysis. So remember, first we compute those expected frequencies, and we can use this formula to find those expected frequencies. This is where we're just going to round to one decimal place to make things easier because we're dealing with these really big, ugly numbers. So let's find this value right in here because we want to figure out how would these numbers be distributed if indeed there was no relationship at all between whether you take hormones or not and if you have heart disease or not. How would those numbers be distributed if there was no relationship at all? So in order to find this value right here, remember this is cell 1, cell 2, cell 3, cell 4. If we're looking at cell 1, here's the row of interest, here's the column of interest. So we want to deal with those totals, and then we'll divide by our n. So we're just using this formula right here. Let's find this value together. So pull out our calculator. We're going to take the total for the row, 8,506. We're going to multiply that by the total for the column, 286. We get a huge number, so let's just leave that in our calculator, and then we're going to divide by 16,608. So divided by 16,608 equals 146.47. Let's just call that 146.5. Okay, so right here is our first expected frequency, 146.5. Let's work on another one together, and then I'll just move ahead. You could kind of replicate the other ones on your own. Let's deal with this one right here. Now we're dealing with this row, so we see this total, this column, so we see this total. We're going to use that in our formula. So let's take the row total, 8,102. We're going to multiply that by the appropriate column total, which is right here, 286. That equals an enormous number. We'll just leave that right in our calculator, and now we will divide by our overall n, 16,608. That equals 139.52. Again, let's just call that 139.5. So we stick that in. If you use that same formula, you can easily find these other values, and that would come out to these numbers that you see right here on the screen. So now we have the observed and the expected values. Of course, you can just stop the video, compute them on your own, and verify that you can get those numbers. Now, once we're done finding the expected values, we can compute our chi-square statistic. So here are the actual observed values. Here are the values that we would expect if there's no relationship between hormone use and coronary heart disease. So are the differences big between these sets of numbers? If they are, it would represent some pretty good evidence that there is a relationship between hormone use and heart disease. If the differences between these sets of values is not large, it would be good evidence that there's not a relationship between hormone use and heart disease. So let's go through the chi-square test. Here we'd have the numbers based on that first step. Let me just walk through them real quickly. So remember, this is saying take the observed value, subtract its associated expected value, square that difference, and then divide by the expected value. So if you number your cells like I typically do, 1, 2, 3, 4, you can see how those match up with these cells, 1, 2, 3, 4. So we take the observed value, 164, there's the observed value, 164, subtract the expected value, 146.5, there's the expected value, I'm subtracting 146.5. I'm squaring that difference, and then dividing by the expected value, 146.5. Now we just keep doing that with every other set. So here's cell number 2, observed value, 122. There we see it. Subtract the expected value, 139.5. There we see it. Square that difference and divide by 139.5. So here I've laid that out for the remaining cells. So that would move us on to this next step where we would see that we would have 17.5, that value squared, divided by 146.5. Here we'd have negative 17.5, that value squared, divided by 139.5, and so forth. So now we can just go ahead and work out those values. Let's go ahead and look at each one of these fractions independently. So let's look at the first one. So here I'm going to take 17.5 and I'm going to square it, multiply by 17.5. That equals 306.25. So we're going to find that numerator in each one of these fractions. 306.25 divided by 146.5. That equals 2.09. All right, so this fraction right here equals 2.09. To that we need to add this fraction. Let's work through it. We have 17.5. I'll go ahead and make it negative just so I'm clear with what we're doing. We're going to square it, so that means we're multiplying by 17.5, but a negative value. And of course, that's going to equal a positive value, 306.25, just like we thought. So each one of these numerators is going to equal 306.25. It's just a good way to check your work. Then we will divide this one by 139.5. 139.5. That equals 2.19. Actually, 2.195, we'll round that to 2.20. Okay, let's move along. So here again, we have 17.5. I'll make it negative. We're going to square it, so that means we're going to multiply by a negative 17.5. Of course, that's going to equal 306.25. And now I'm going to divide that by this ugly number, 8,359.5. That equals 0.036. We'll call that 0.04. And then finally, right over here, we have 17.5. We're going to multiply that by 17.5. That equals 306.25. And we're going to divide that by this number right here, 7,962.5. That equals 0.038. That also we will round to 0.04. Okay, so that brought us right here. If we take these values that we just computed, when we now add them all up, we find a chi-square value of 4.37. That's 2.09 plus 2.20 plus 0.04 plus 0.04 equals 4.37. So again, that was a lot of work, and particularly when we're dealing with real-world numbers, it just takes, a little bit more time to punch them into our calculators. Well, now that we have those numbers, let's determine if we have statistically significant results. Let's make more sense of this data. So again, we need to ask ourselves, how big does that chi-square value need to be? We just found a chi-square value equal to 4.37. This is just a reminder that we're always dealing with 1 degree of freedom because we have 2 rows and 2 columns. The ways we figure out degrees of freedom, take the number of rows minus 1, so that would equal 1. Take the number of columns minus 1, that would equal 1. We multiply those two values. 1 times 1 equals 1. We will always have 1 degree of freedom. And when we do for a 2x2 table, these will be our critical values. So if we have a critical value of 3.841, our chi-square value does indeed exceed that. But you can see that our chi-square value does not exceed the value that's used for a critical value when we have an alpha of 0.01. So we can summarize things, I guess, this way. We found that our chi-square value is equal to 4.37. So we are finding that the observed and the expected frequencies differ significantly from what we would expect by chance. It's statistically significant at the 0.05 level, but not at the 0.01 level. And we'll talk about that just a little bit later because it's kind of an interesting little side tidbit. So let's take this data and put it into that 4-step hypothesis testing procedure. Before we do that, let's talk about this real quickly. Of course, we want to make sure we understand the direction of the results. So here we're able to say that hormone use is statistically significantly related to heart disease, but in what direction? So here I started computing some percentages. That's the only way we can really make sense of things. So I want to know, of the people taking hormones, how many of them have heart disease? That's 164 divided by 8,506. Let's compute it real quickly. 164 divided by 8,506. That equals 0.019. If we look at that in terms of a percentage, you can just take that decimal place and move it to the right 2 places. So that's like 1.93%. So I've listed that right here. Let's figure out the percentage of people in the control group who had heart disease. There were 122 people out of 8,102. So here we take 122 and divide by 8,102. Again, let's list that as a percentage just because it's a little bit easier for us. I'm just going to take this value, move the decimal place 2 to the right, and I see 1.51, it looks like, if we do a little bit of rounding. So I'll list that right here, 1.51%. So we can see that the people who took the hormones were indeed more likely to have heart disease than the people who took the placebo, the people in the control group. So people taking the hormones more likely to have heart disease compared to people taking a placebo. But look, that's not a huge difference. And this is another important point that we make, that statistically significant differences don't necessarily mean big differences. It just means that the differences that we found are very unlikely to occur just by chance. So when you measure 16,000 plus people, it's very unlikely to find a difference, even that small, just by chance. So this was kind of an interesting example because this study has had a huge impact on women. Many women stopped taking hormones because there was an increased risk of heart disease. But if people really understood statistics and they really looked at these percentages, they might not have been as scared. Do hormones increase the risk of heart disease? Absolutely. We found a statistically significant difference. Is the difference all that big? No, it's not necessarily all that big. So now let's go ahead and formalize that in our 4-step hypothesis testing procedure, where we will conclude that hormone users are indeed more likely to develop heart disease. So here we have all that information that we just talked about. We'll state our hypotheses. Remember, the null hypothesis is that chi-square is going to equal 0, because in everyday language that means there's no relationship between hormone use and heart disease. Now our alternative is that the chi-square value is going to be greater than 0. There's going to be a departure, in other words, between our expected data and our observed data, which would show that there's a relationship between hormone use and heart disease. So we have these two competing hypotheses, and we want to figure out if we have enough evidence to reject the null. We collect the evidence. Well, we've already done that. We computed a chi-square value of 4.37, so we'll list that right here. Now we want to compute the probability of finding that data just by chance based on our null hypothesis being true. Well, I'm asking us to compute this using an alpha of 0.05, so we'll use that as our critical value. Our critical value is set at 3.84. We can see that 4.37 clearly exceeds that critical value. It's in our critical region, otherwise known as a rejection zone. So we were able to reject the null hypothesis. We were able to conclude that we have statistically significant results because the probability of finding a chi-square value in here will happen less than 5% of the time. The probability is less than 5%. So we find that the probability of finding this result by chance is less than 5%. In other words, the result is statistically significant at the 0.05 level. So we're going to reject that null hypothesis because our value was in the rejection zone, and we'll conclude that hormone users are more likely to develop heart disease. So I'm formally rejecting that null hypothesis and taking on the alternative, saying there is a relationship between hormone use and heart disease. Specifically, hormone users are more likely to develop heart disease. Now, one reason why this is an interesting test is because typically, you've heard me say, in medical journals, they require an alpha of 0.01. Here, this was statistically significant only at the 0.05 level. It was not a statistically significant result at the 0.01 level, which has always left me kind of scratching my head. So, with that in mind, that pretty much sums up everything that we needed to know about section 10.2. For now, that is all.